We come now to one of the most important topics that we'll study this semester, and probably one of the most important topics that you'll study in your whole education as an engineer or scientist. Now that's a pretty big claim, and I want to spend a minute talking about it. Why do I say that these laws are so important, that they're one of the most important things that you'll study? Let me give you 3 reasons. I'll write them down, and then we'll come back and talk about them. 1, Newton's laws are really foundational. We'll come back. Also, these laws apply all over the place. They apply to so many systems that we can consider them to be universal. And 3rd, because of these 2 things, Newton's laws really permeate the way that engineers and scientists tend to see and think about and consider the world around us. So I'm going to write here that these laws are permeating. Newton's laws are sunk pretty deeply into the brain and the thinking habits of most scientists and engineers. Newton's laws involve forces and how things react to those forces. And if we are considering a mechanical system, most of us very often think about it in terms of forces. All right, let's come back and talk about this foundational point here. There are 4 basic approaches to the topic of mechanics, the study of how and why things move. I'm going to list them here. 3 of them, as it turns out, are either Newton's laws or repackagings of Newton's laws. So here they are. The first is just straightforward Newton's laws. So that's one way to study mechanics, is to just apply Newton's laws to them in a straightforward way. After that, we'll get into, in this course, what's called work and energy. It can often be convenient to repackage Newton's laws, Newton's second law in particular, and take advantage of certain things about it to give us a convenient tool for studying motion. And that leads into this topic of work and energy. It's really nothing but Newton's laws repackaged in ways that can be, in some cases, more user-friendly. There's a third approach that is called momentum. And it is certainly nothing other than, again, a different repackaging of Newton's laws. These 3 things take us through our entire study of translational motion. So that's most of this course. So most of what we're going to do the rest of this semester comes straight from Newton's laws. There's a 4th approach to mechanics that we don't study in this course, but you might see in a later course. And it's essentially independent of Newton's laws. And it's called Lagrangian or Hamiltonian mechanics. You might study this in a later course, but for what we're going to do this semester, there's no question that Newton's laws form the foundation. You need to have a good understanding of Newton's laws and how to apply them to follow along and do well with the rest of what we're going to do this semester. All right, point 2. These laws are universal. They apply all over the place. If in your work as an engineer or a scientist, you are studying a mechanical system, some system with mass, pieces, and parts, and you want to know how or why they're moving the way they are, or you want to control or limit how they're moving, Newton's laws will apply to that system. You can apply this to almost anything in the world. And again, because of these first 2 things, these laws really tend to permeate the way that we as engineers and scientists see and think about and deal with the world around us. All right, so that's a bit about why these laws are so important. Let me do this now. Let me write these 3 laws down, and then I'll stop the video, and in the next one, we'll start talking about each one in particular and seeing what it tells us about mechanics. All right, so let's write down Newton's 3 laws. The first law, the second law, and the third law. The first law is most often said as a big, long, kind of confusing sentence. So I'm going to say that sentence, and then we're going to condense it down into a mathematical statement. So it often gets said something like this. An object at rest remains at rest. An object in motion remains in motion at constant speed in a straight line unless an outside force acts upon it. Okay, big long sentence, and there's no way I'm going to write all of that down. Let's see if we can condense it down to its essence and write it as a mathematical statement. The first two parts of that sentence have something in common. The first part was, an object at rest remains at rest. The second part was, an object in motion remains in motion at constant speed in a straight line. Those two parts have something in common. The first part is not moving. It has no velocity. An object at rest remains at rest. The second part is moving. It has a velocity, so that's not common. But notice that neither of them has any acceleration. An object at rest remains at rest, no acceleration. Its velocity is not changing. It's zero, and it's not changing. The second part says, an object in motion, it's got a velocity, remains in motion at a constant speed in a straight line. It's got a velocity, but that velocity is not changing, so it has no acceleration. So that whole bit, the first two parts of that big long sentence, really says acceleration equals zero. There's no change in velocity. The rest of it says, unless an outside force acts upon it. So I'm going to write that as acceleration is zero if the outside force is zero. All right. Now this law tells us that apparently there is a thing in the world called a force, and that force causes accelerations. If there is no force, there's no acceleration. So we can suppose then that if there is a force, then there must be an acceleration. It doesn't tell us what a force is or how much acceleration there's going to be. There's a few things we can dig out of the first law, but the thing it tells us on the face of it is that there's this thing called a force, and it's responsible for changing the motion of an object. Let me say a little bit about what a force is and why I'm using this notation with the sum of the forces. Okay, first of all, what is a force? Imagine we have a box or a crate or something. I'm going to take my high school teacher's definition of force, which was a force is a push or a pull. Suppose I push or pull on this box. I'm going to exert a force. I'm going to call it F1, and that's me pushing on the box this way. It's a vector. The length of it tells me how hard I'm pushing or pulling, and the direction says I'm pushing this way, not some other way. Okay, so this is a vector quantity. It has a magnitude and a direction. So that's what a force is, a push or a pull, and what it can do is apparently change the way an object's moving. Now why do I put this summation here? I put this summation because what's important if you want to know how an object's going to move is not a force that's acting on it, but the combined effect of all of the forces. There might be other forces acting. I'm pushing or pulling this way. My little brother might be pushing or pulling this way. I'll call that F sub B. There might be gravity acting on this thing, force of gravity here, and I don't know, maybe the wind is blowing and putting a force on it this way. There could be all kinds of forces acting on this thing, each of them pushing and pulling in a certain direction. If you want to know how the object's going to move or what the result of all this is, you have to add all of these forces together. So when I write this, it means the same thing as the net force. What's important for how an object moves is not an individual force, it's the net effect of all the forces. So I'll usually write it as the sum of the forces. It's the same thing as the net force. Alright, we'll come back and say a little bit more about Newton's first law in the next video, but for now, let's leave that one there. The second law is of massive importance, and it is the one that we use all the time. It tells us if you do add all the forces up acting on something, what it equals is the object's mass times its acceleration. Okay, This is the first time we have talked about mass this semester. Let me add here that this equation is only valid if the mass is constant, if it's not changing in time. So mass needs to be constant to use this. Later in the course, we'll talk about what happens if mass is not constant. But as of now, we haven't even defined what mass is. That'll come up in the next couple of videos. What this equation does, though, is it relates for us the cause to the effect. If you have cause of some motion, a net force acting on an object, Newton's second law will tell you how much acceleration you're going to get out of it. And it's going to turn out to be inversely proportional to this mass. Okay, that's the second law. We'll come back and do a whole lot with it as we move along. Newton's third law tells us that forces always come in pairs. I'm going to write it and then we'll talk a bit about it. The force that one object exerts on another object. So this is the force exerted by object A on object B. Newton's third law tells me if object A pushes or pulls on object B, then object B pushes or pulls back on object A. So B is going to exert a force back on object A. And these forces have the same magnitude in the opposite direction. Forces always come in pairs. We'll come back and talk about Newton's third law in some detail. But for now, let me leave this here, and the next video we'll talk about Newton's first law, then we'll talk about Newton's third law, and then we'll spend a whole lot of time talking about and applying Newton's second law.